last class was we did Legendre transformation, okay, and what we found was you could define a new function p q dot minus L, and then we said that we can use this particular function, which is the Hamiltonian, to write down the canonical equations, which is q dot equal to del H del P and P dot equal to minus del H del Q. And this is nothing but equivalent to Newton's laws in specific cases. And H for conservative systems, H is just T plus V, as simple as that. And then we said this geometrically means that any system's full state can be represented by a point in the phase space, and as time evolves, P and Q of the system will evolve. That means from some Q naught, P naught, you will go to some Qt, Pt, and some trajectory. These trajectories have to be unique. These trajectories cannot cut. This is associated with this philosophy of determinism, that it was propounded in some form by Laplace probably in 1600s or 1700s, that same cause has same effect. Right? That's what you think. Same cause, same effect. You repeat the experiment with the same cause, you get same effect, and you mathematize that thing by writing down equations which follow that thing. Same cause means you have same Hamiltonian. Same effect means you get the same prediction for Q and P. And then we said the most powerful thing of Hamiltonian formalism is what are known as canonical transformations. Canonical transformations are such transformation that you go from QP to some other coordinate QP such that you get Q dot equal to del K del P and P dot equal to minus del K del Q, where K is the Hamiltonian in the new coordinates. If we can perform such a transformation so that K becomes very simple, then we can solve this trivially. We know what Q is capital P is, and then we can transform back to small q and small p, and we have the answer. Okay? So that's what we did. So any questions there? Any kind of question? Nothing? Okay. Fine. So our goal is to find out which kind of transformation is a canonical transformation. In general, you can write any transformation of this form. Again, to emphasize, we are only doing 1 degree of freedom system and time independent system. All these concepts can be extended. The mathematics just will become more complicated, that's all. The proofs will become a bit more complicated, but other than that, the main concepts won't change. So this is a type of transformation. It could be, you see, examples could be e to the power p, log p, this could log q, this could be, let's say, q square plus p to the power cube. This is a kind of transformation. You can have other transformations. You can have p to the power 4 by cos q, and you can have a trivial transformation here, p negative. You put anything you wish. In fact, you can also go to complex plane, define complex transformations. Those are also possible. So all I'm saying is you can do any kind of transformation you wish, but we are only interested in those transformations which keep the canonical structure. This I am calling canonical structure. More technically, this is known as symplectic structure intact. Okay? So this canonical structure we want to preserve. So let's see the proof, or let's find out the conditions. Okay. We also discussed some other things related to Poisson brackets. So what was the Poisson bracket? This is nothing but del f del q del g del p minus del f del q del g del p, yeah, the other way around, p del g del q. Given this definition, it's easy to see that f will be 0, gf will be minus fg, right? And also we found out if f comma g are first integral of motion or conserved quantities, then fg is also a conserved quantity. Okay? That's what we had found out. So now we will require all that to find out the condition that when a transformation is canonical. So let's start. We had one more thing here, the Poisson theorem, that any quantity u dot, so this is one point, this is another point, this is another point, this is, we also had found u dot is nothing but u comma h, right? That's what we had found out, where u is a function of p and q. Okay. So we are saying from here we are going here. Here the Hamiltonian is h. H will be a function of q and p. If I do the transformation, this Hamiltonian can be written down as h of q of qp. It's the inverse transformation. Q can be written in terms of capital Q and capital P, and P can be written as capital Q and capital P. So that's how you can write. Now if you want to symbolically denote it as a function of Q and P, because this is what H is depending on, you have to mathematically use a new function. That's all. It's just a symbol. Is this understood up to here? We are saying if you do the transformation, the H will go like that. Then if you redefine a function, I cannot use H here technically, though physicists are used to using H and keep things in mind, though the functional form is not same. We do that, but here we will be a bit more precise, otherwise doing calculation will be hard. We will mess it up. Okay, okay up to here? Now let's proceed. Q dot. What is Q dot? Forget about all this. From here, Q is a function of small q and small p. Capital Q is an arbitrary function of small q and small p. That means, in accordance with the last point there, this is nothing but this. U is any arbitrary function. So you can write this, which if you expand, this is how it's going to look like, right? Now, let's look at this term and this term. Now, what is del H del P? Del H del P is of course Q dot, but what we are after is we want to write this in the form del K del capital P. That's what we want to do. So we have to get rid of all the small p's, small q's from here. That's the target. So we are going to transform this. We are going to rearrange this. Now this H is nothing but this K actually. So, I am going to write it down as this. K is a function of these two things. So, now I do simple chain rule. This means del K, del Q, del Q, del P plus del K, del capital P, del capital P, del small p. Simple chain rule. Okay. Now, I take this. Okay, I need one more. I need this one. Del H, del Q. That will again be del K, del Q, which will be nothing but by chain rule del K, del Q, del Q, del Q plus del K, del capital P and del capital P, del small q. Is that right? So, now I take these things, plug it in here. Take this thing, plug it in there. So, let us write it. So, q dot is now del q del q del k. Okay, let me write it in this fashion. So, I am going to write this first, then I will write that. So, I have del k, I am writing this down first, del q, del q, del p, and with this term this comes. So, del q, del right, plus del, again I am going to write this, then I will write the first term over there, del k, del p, del p, del p, and del q, del small q, right? Okay. Now, this thing minus del q, again I will write this one first and then I will write this. Okay. So, del k, del q, del q, del p, okay, and what should I write now? Del q, del p, right? This one. Now, again I write this for this and then I will write that one. So, minus del k, del p, del, is there something wrong? This should, that is fine. No, no, I am going to write this. So, first I wrote this, then I wrote this. So, this is nothing but this, which looks, this one. No, no, what are you saying? Del q, this one. Ah, I am using the wrong thing, yes. So, this is what I have to use. So, del q, thanks, and then comes this. So, now it is okay, right? And now I have to use this and use it here. So, again I am using del q, del p, that is right. That seems right, and small q, and I am left with small p. Okay, looks okay. Wonderful. So, now these two together, I can take del k, del q common. What is left is del q, del q, del q, del p, and then with a minus sign q and p flipped, which is nothing but, which of course is 0, but let us write it first in terms of Poisson bracket. So, everybody okay with this? I am just using the definition of Poisson bracket. Similarly, here with a plus sign, what is left here is del k del p, and so this q comes first, then del p, then this thing is flipped, so it's nothing but q comma p. Right? Good. So similarly, one should do for capital P dot. I leave that as an exercise. I am guessing, well, I am guessing because I know, but I am not sure about the signs a bit, so I will play around with it. But it has to be something like del H del Q, this will become P comma Q, and this will be del K del P, P comma P. Okay, this is something you should check. So check this. I am more or less sure that's the right answer. So you understood the first part, the derivation of first part. Second part is similar. You have to play around with partial derivatives and chain rules. Okay. So if you have understood, I am going to rub this. And then by looking at this, I want to find out the conditions so that I get the canonical structure back. So what should be the condition? What do I want? I want q dot should be equal to del k del p. That means I want q q equal to 0, and I want q p equal to 1. Because then you get the canonical structure back, q dot equal to del k del p. From the second equation, you want p q equal to -1, because p dot is del k del q with a negative sign. That is the canonical structure. And you want p p equal to 0. See, out of this, this and this are same by definition of points of brackets. If I flip it, a negative sign will come. So I don't care about this. Though these are trivially satisfied, I have still written them because when you go to higher degrees of freedom, then these conditions will be modified to qi qj, pi pj. In that case, they are not trivially satisfied. But for 1 degree of freedom, it is trivially satisfied. So in general, 3 conditions have to be satisfied. Okay. But for 1 degree of freedom, this is trivially satisfied. By definition, QQ has to be 0. I don't have to put it to 0. PP has to be 0. I don't have to put it to 0. Why PP and QQ are 0? Simply because of this. So the only condition which is left is this. Now note, this is something important and screwed up in some of the books. If I expand it, this is going to look like del capital Q, del Q, okay, let me write it down this, and then you, suppose I write this. A determinant, when you calculate this determinant, what is this? This times this minus this times this, which is nothing but the points of bracket. But this is valid only for, you know, this particular case. You can write it in nice determinant form. What do I mean by that? You can always write it in that form. It's just by definition that, okay. And what is this? This is nothing but the Jacobian of this transformation. So usually in some of the books, this is where it's somewhere it gets wrong, if you are not reading right books, you will find the statement that Jacobian being 1 is the necessary and sufficient condition for a transformation to be canonical. Okay. But that is not right. Jacobian being 1 is only necessary condition. Only for 1 degree of freedom cases, Jacobian being 1 happens to be necessary and sufficient condition. The necessary and sufficient condition is all the conditions have to be satisfied. But for 1 degree of freedom, as it happens, other conditions are trivially satisfied. You are left with one condition, so that becomes necessary and sufficient condition. So you calculate Jacobian, if it's 1, then the transformation is canonical. Need not be so for higher degrees of freedom. You can, I mean, it's a necessary condition, so it's not a sufficient condition. You have to keep that in mind. But that's subtle. But for us, because we are not going to get into these subtleties, all we have to find is whatever transformation I give you, you just calculate the determinant of the Jacobian. And if that is 1, then the transformation is canonical. What does that mean? If that is 1, it is possible to find out a k such that the canonical structure is preserved. Very important point is this. In this derivation, I started with an arbitrary Hamiltonian. I did not use specific form of Hamiltonian. So canonical transformation has nothing to do with what Hamiltonian you are starting with. Doesn't matter what Hamiltonian are you starting with. Okay. So if I give you a transformation, it's either canonical or not canonical just by virtue of these conditions. It has nothing to do with Hamiltonian. So canonical transformations are way above. This sometimes you get confused. You think canonical transformation only in context of Hamiltonians. True. The way it's defined is that the canonical structure is preserved. But which transformations are canonical and which are not has nothing to do with what Hamiltonian you are working with. Great. So what we have found out, if this is satisfied, then you have a canonical transformation. So now all that is left to do is, can one find out a transformation which is such that k is very simple? Okay. Because if k is simple, you can solve the problem. By the way, as an aside, just note a trivial thing. By virtue of this, what will be h comma h? 0. And by virtue of this, it means h dot equal to 0. That means Hamiltonian itself is a constant of motion for a time independent Hamiltonian system. So you already have one constant of motion, and because it's usually the total energy T plus V for conservative systems, so it's intuitively also okay because energy has to be conserved. Okay. So 1 degree of freedom system can always be solved, because 1 degree of freedom system will how many first order derivatives? I mean, how many first order equations? 2. So how many conserved quantities you need to solve the problem? 1. 1 less than the total, and 1 you always have. So 1 degree of freedom Hamiltonian systems are trivial. You can always solve them. They are always solvable. You always know the answer. It may be mathematically complicated to go through the jugglery of doing different algebra, but it's always solvable. It's never a problem. The problems will start when there will be 2 degrees of freedom, 3 degrees of freedom, and although it's Hamiltonian, you will have only one conserved quantity in your view, which is going to be the Hamiltonian. Where is the next one? That will screw up the entire thing. So now let's see an example of how to simplify the Hamiltonian and then solve the problem. Okay. So let's say I have a transformation pay attention to the flow of logic. I am using this, I am not talking about Hamiltonian at all when I am writing down the transformation. Okay. So, that way you already are seeing the transformation has nothing to do with Hamiltonian. Even without looking at Hamiltonian, I can ask the question whether this transformation is canonical or not, because I am after canonical transformations. So, how to check that? I have to check this. To check this, let us first write down Q. So, what is going to be Q? So, I divide and then take, so this will be tan inverse Q by P. What will be P? If I square both the sides and add them up and then divide, so P is going to be is that right? So, that is Q. I just did inverse transformation. Now, I have to find out whether this is canonical or not. How to do that? I have to find out this determinant. So, what is del Q del Q? That will just be, so what is the derivative of tan inverse x? 1 over x square, right? So, this is 1 over 1 minus 1 plus q square by p square, and the derivative of the inside thing is going to give you 1 over p. That is the first derivative. The second one will give you again 1 plus q square by p square, and the upper one is going to give you minus q over p square. Del p del q will give you q. Del p will give you p. So, now this is nothing but this times this and this times this. Let us do a little bit of jugglery right here. So, this p square I can write here. So, p square will go up, this will just become p. Similarly, here p square can be written here, that p square will go up and you will have minus q. And now, you can straight away see this times this is going to be p square by p square plus q square. This times this is going to be q square by p square plus q square with a minus sign. When you take the determinant, there will be minus, that minus will go with this. So, you will have p square plus q square by p square plus q square, which is nothing but 1. Nothing to do with Hamiltonian, nothing here, it is just trivial maths. So, we have found out this transformation is canonical. Is this helpful? So, let us solve the problem of simple harmonic oscillator using this technique. So, what is the Hamiltonian of simple harmonic oscillator? If we ignore all masses and I mean all the parameters we set to 1, then it will just look like, that is what it is, x square and momentum square. We did this problem in the last class. Now, you set all m, l, etc. to 1, q is the generalized coordinate. P is this. Okay, we will work with this. As an aside, let me hint something before I forget it, which is this. There is a huge advantage of using, not quite advantage, well, it depends at what level of formalism you go. At some point it starts showing up, the advantage is this. You see, you are saying q is generalized coordinate, p is generalized momentum, right? Right, what was I saying? That q is the generalized coordinate and p is the generalized momentum. Now, I am saying I can make canonical transformations and rewrite the Hamiltonian. Suppose I come up with a transformation like this, q equal to p and p equal to minus q. First question will be, is it canonical? So, let us check. Del q is going to be 0. del q del p is going to be 1, del p del q is going to be -1, and del p is going to be 0. This is nothing but 1. So this is a canonical transformation, which means if I take an arbitrary Hamiltonian, do this transformation, then I will get a new Hamiltonian and I'll get the canonical structure back. Standard meaning of what we were discussing. But note, now here we have problem with nomenclature. Here, when I'll use, after doing this transformation, when I write the new Hamiltonian, note, your coordinate has become momentum, and momentum has become coordinate. Now, it's really hard to say what is momentum, what is coordinate in Hamiltonian formalism. That's why in Hamiltonian formalism, it doesn't make much sense to talk about generalized coordinate, generalized momentum. You say you have canonically conjugate coordinates. So both q and p are conjugate coordinates. They are conjugate to each other, okay, in literal sense, in linguistic sense. And whichever you take, it's fine. Don't say one is momentum, the other one is coordinate. That distinction is no longer needed. Okay, so this is something you should keep in mind. So sometimes I may use the word, use the phrase like this. So we are writing the canonical equations of motion in canonically conjugate coordinates. I don't want to say I am going to write down the canonical equation in terms of generalized coordinate and generalized momentum, because the nomenclature is messed up now. Is this understood? It's just a remark. So let's come back to our problem. Now I'm going to solve this problem. What is meant by solving? I want to predict. That means I want to write down equation and write down the solution. I want to solve this problem using these formalism. It will be like holding your nose like this, okay, or maybe right from here and there. It's as bad as that, because one can solve it as simply as possible, right? Just write Newton's laws and done. Why would you do that? Doesn't make much sense. But I mean, just to get used to this thing, what's the use of this formalism, that can be highlighted by this simple structure. And as I said, to understand a concept or a structure or something, you should work with the simplest possible case. So let's work with this. Okay. So what is it that we are trying to do now? We want to find out nu k such that the canonical structure is there. From here, I know what is q dot. What is q dot? Q dot is q, and p dot is p square, right? I'm going to walk out of the door if you don't answer this, because then there is no meaning. Is that right? So what's right? You see, if you don't speak up in your class, in your college, you are not going to learn, unless you are super genius. Stop being shy and say something. P dot equal to P. Why? Del H del Q, as simple as that. What is P dot? Okay, that's what you have. Keep that in mind. Now let's find out Q dot. Q dot is nothing but dot of this. So that now is going to be 1 plus q square by p square, q dot by p, minus because I will have 1 over p square. So you have q by p square times p dot, right? Let's put p dot here, and this will be 1 plus q square by p square. Is that right? Looks okay. So let's massage it a bit. So this p square I can take here, that P square will go up and it will become P q dot. Similarly, this P square will go here, that P square will go up and then this will become Q P dot, right. Now, Q dot is P, P dot is minus Q, this is just breaking down. So, this is nothing but 1. Good. Let us find out P dot. That means ddt of this, which is as simple as that, Q dot plus P dot. No, that is wrong. Q q dot P p dot. Q dot is P, so Q P. P dot is minus Q. I am interested in finding out whether this can be written down in this fashion. That is what I want to know. So, now how to find out K? This is nothing but a simple partial differential equation. This is a simple partial differential equation. So, if I solve it, then K is what? What is the general solution of K here? P plus some function of Q. P plus some function of Q. If I solve this part, this will be some function of P. This satisfies. This equal to 0 is satisfied and this equal to 1 is also satisfied. Now, both have to be simultaneously satisfied, which is only possible if this both thing does imply. So, what is going to be the solution? They both have to be simultaneously satisfied. So, capital K is this, capital K is this. That means, this has to be function of P, okay, which is equal to which is this. So, I can already see function of P is here. So, this has to be P. I see here there is no function of Q. So, this has to be 0. So, the only way out is, of course, you can add constants. Those are never interesting, because you see adding constant is like shifting the datum line for calculating potential energy, nothing more than that. So, this is K. We have found out what is K, and we have found out that you can write Q dot as del K del P and P dot equal to minus del K del Q. Now, see, it is very easy to solve now. You know Q dot is 0, Q dot is 1. So, what is the solution? What is capital Q if capital Q dot is 1? You see, if you say slowly, answer is right, it is going to remain right. If you say loudly, if answer is right, it is going to remain right. So, no point, I think TechCube is feeding you well, so no point conserving your chemical energy. So, Q dot equal to 1. What is Q? Equal to some P plus some constant, maybe at most, right. What is the solution if I try to solve this? P dot equal to 0, P equal to constant, some constant. Let us put some constant, maybe B. K is probably better. So I've solved the problem. Because Q, I now know Q is this, P is this. Now recall, what was Q? Root 2P sine Q, which means this is nothing but 2K times sine T plus C. What is P? P was, which means this is nothing but, that's how simple harmonic oscillator behaves. We have solved the problem. But now see, solving the differential equation is trivial, because solving this is trivial. Why is it so? Because I could come up with a transformation which was such that K could become simple, and I solved it. This is okay up to here. You have to go through this problem by yourself, little by little, try to understand each step, appreciate what is happening. Just keep the big picture alive. The big picture is you want to solve a problem. Solving a problem can be hard if your equations are hard, nonlinear, etc. One way of tackling it is, can I construct a new Hamiltonian such that the equations of motion becomes trivial? That's what you are trying to do. But no, to all this, I had to predict what is the transformation, right? I mean, what is the transformation? How did I know the transformation? Because before coming into lecture hall, I memorized it, and I came, I wrote it down. It's as simple as that. How did I come up with the transformation? It was written in some book. How did the transformation come to the guy who wrote the book? Maybe he copied from some other book. Usually that's what happens. Right? But the whole idea is, you really don't know which transformation is going to work, which one is not going to work. If you come up with it, you come up with it. If you don't come up with it, just play around with it. What can you do? So you will get very rare examples where the transformation can be found so trivially that you can solve the problem trivially. Message is something like this. Once a problem is stuck in Newtonian formalism, chances are it's going to get stuck in Lagrangian formalism, it's going to stuck in Hamiltonian formalism, because at the end you have to solve the problem. And you know, at the end you get the same kind of equations of motion. So once you are stuck in solving equation of motion mathematically, you are always stuck. Mostly. But still sometimes it's going to help you. If you can take this formalism further and further and further and try to come up with the method of trying to find out the transformation. So here the message is this. If I can come up with the transformation which makes the Hamiltonian simple, I will do that transformation. But now the question is how to find out the transformation. So from here the theory goes to something known as Hamilton-Jacobi theory, which we are not going to do at all. But the Hamilton-Jacobi theory does this. So now think like this. So this guy was talking about walking on the ramp. So now think about Hamiltonian. There is a world where there are only Hamiltonians. Okay, and we are conducting a Mr. Classical Physics competition. And all the Hamiltonians are walking. And you are going to have all this thing, the 7 point, 2 point, or whatever. And then you have to pick the most beautiful Hamiltonian. So which Hamiltonian is most beautiful for you? Sorry? You said something. I mean, why do you, at most you will be wrong. So what Hamiltonian will give you the easiest equation? What is the most simple Hamiltonian? 0. You should be proud. 0 came in India, so you are sort of saying, 0. 0 is the most beautiful Hamiltonian is Indian. Because it's 0. India gave 0, something like that. Right? So you want your transformation to be such that K is 0. If you can do that, then you have solved the problem. But to find that out, you have to find the transformation. So now the question becomes, for what transformation Hamiltonian will become 0? And in order to answer that, what happens is, you get an equation. So this is something we are not doing at all. I'm just telling you the big picture, and then you can this is the action S. Everything will, come in together. Whatever you have learned, everything will come up in the Jacobi, Hamilton-Jacobi theory, where now finding transformation is equivalent to finding a function S, which will be a generating function. Note, you see, this transformation Q equal to P, Q equal to Q, and P equal to P. This is an trivial identity transformation, right? Is this a canonical transformation? It always will be, because you are doing nothing, no change. So your Hamiltonian structure will preserve. And before saying yes or no, you could have just calculated the Jacobian. It will be 1. So this is a canonical transformation. But another way of writing this is nothing but Q and P. So this becomes, you will probably not understand, you will be uncomfortable with this, but I'll still write it so that you get a flavor. Wait, I'm messing up something here. Note, I can write Q as del capital P of Q capital P. I can write capital P as del Q of small q capital P, right? This is known as a generating function. So it's like either I give you the transformation or I give you this function and this relation. It's equivalent. Giving generating function or giving the transformations are equivalent. So that's what is happening here actually. Here you are not writing the transformation, you are writing S, which is actually the generating function, such that it generates the transformation for which k is 0. Something like that. So all I am saying is, the best Hamiltonian is k equal to 0. To find it, one has to solve set of partial differential equations and find out, it's not a set, it's a single partial differential equation. And then you have to solve it, find out S. If you can find out S, you can find out the transformation. If you can find out the transformation, you can write down the canonical equations, and then you can solve it trivially, everything is done. Okay? But there will be complications there also. So that's how everything is developing. And there, if you cannot solve it, then you come up with what are known as perturbation theories. Perturbation theories are again very simple. Just to give a hint of it, I'm not going to do it, but forget about differential equations. Okay. Suppose I give you an algebraic equation like this and ask you to find out x. How will you find out x? You know that formula, right? Minus b. Suppose you don't know that. No, but that's the formula. Completing square is the formula. No. So the idea is this. Yeah, you can keep on doing trial and error, but you don't have to do trial and error. The idea is this. If epsilon is very, very small, then you will expect the solution of x, the solution to this equation, the value of x will be very close to c. So you assume, you give an ansatz that my solution goes as c plus epsilon times x1 plus epsilon squared times x2 plus dot dot dot. Because that's how solution should be. Because when epsilon is 0, your solution should be just c. When there is little bit of epsilon, solution will be modified. Whatever is the solution, because epsilon is small quantity, you can sort of Taylor expand it. So, this is the form of yours. Then you will take this, plug it in back here, compare the coefficients of epsilon, epsilon square, epsilon cube, you will get solutions for x1, x2, x3, x4, dot, 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 dot. And you plug it in and you find out, okay, that's the solution of x perturbatively. Okay. So, what happens is these equations become hard to solve, then perturbation theories are invoked, assuming that, okay, nonlinearity is weak, things like that, and then you start doing perturbation theories. And at some point, even perturbation theories fail. This was something which happened in late 1800s, when, now this story I keep on forgetting, but still, I keep on forgetting the names. So there were three guys, this Weierstrass, mathematician, Dirichlet, Kronecker, and Poincaré. So these are four characters in the story. So story is something like this, that Weierstrass, I'm probably pronouncing it wrong, okay, but Weierstrass was trying to find out whether solar system is stable or not. Okay. And it seemed to be a very hard problem, and he made a mess of it probably. And then he was talking to Kronecker. I mean, it could be somewhere around, maybe Kronecker was not there, something, but anyway, let's go with these names. So we start with the caption. All the characters are fictitious, any resemblance is coincidence. So there is no problem now. So now Kronecker said to Weierstrass, oh, my supervisor, Dirichlet, has solved this problem. And now Dirichlet was a serious guy. So Weierstrass was thinking, if Dirichlet has done it, then it must have been done. Now, in the meantime, probably Dirichlet died or something. So now where is the solution? But Dirichlet has said he had solved it, so there must be solution, something like that. And they tried and they could not find any solution, whether sun, moon, earth system is stable or not, something like that. I mean, this was a great theological question, and this was happening in Sweden. So then Weierstrass went to King and somehow convinced him, and it was easy to convince him. You see, now you can pose it as a question of God, whether God has made a universe which is stable, are we going to survive, and things like that. Give me money and we are going to find out solutions. Just seeking research grant the way it goes. But he did something else. He went and he announced a competition that somebody who can solve this problem is going to get some big money. And in this competition, the guy who contributed significantly was the last universalist mathematician, Poincaré. Poincaré, whatever way you pronounce, it's probably Poincaré. Okay. So this Poincaré couldn't solve the problem, but he could see there are problems with the problem. Now, the standard perturbation theories don't work. It's hard to, mathematics just gets crashed. You get terms which are infinities in your calculations. Infinities you cannot deal with. It's hard to deal with infinities. Same thing happened later on in QEDs, say where infinities came and then they had to be renormalized. You know, this Wilson's renormalization group, etc., etc. But they were infinities. Also in QED, QED was not with Wilson. Wilson did with StatMech, but I mean, it's related sort of. But anyway, so there were infinities in the solutions. So it was hard to deal with it. And he was getting weird solutions. But he developed the subject so much that in order to solve that problem, he ended up developing what is nowadays known as algebraic topology. So the entire algebraic topology came because of that study. But the problem remained unsolved. And then in end of 50s or probably starting of 60s, for 9 years, there were three brilliant mathematicians. One of them is still surviving, Arnold. So it's Kolmogorov, Moser, M-O-S-E-R, and Arnold. They wrote sequence of papers in 60s. And they developed what is nowadays known as KAM theory, K-A-M theory. And KAM theory changed the entire way of looking at such kind of problems where infinities crop up. They changed the statement of the question and provided some sort of solution. But still, I don't think the problem is completely solved because it's very mathematically notorious problem. And cam theory is somewhere you reach when you at least start doing. So what you have to do is you have to know perturbation, this canonical transformation. Then you have to go to Hamilton-Jacobi theory. Then you have to go to action angle variables. And there you have to deal with 2 degrees of freedom. There you will, the next step is going to be the cam theory. So it's a little bit further, but it will take time. So if you want to understand what cam theory is all about, you first have to know fair bit of analytical mechanics. But that was hallmark of classical mechanics at that point of time. And the biggest problem with classical mechanics, according to me, happens to be this, that classical mechanics was it in its full blow. I mean, all the mathematicians said everything, every person was doing this thing in early 1900s and before that. But right then relativity came up, okay? And then quantum mechanics, GTR, everything. So people got excited with new things. So physicists stopped working on classical mechanics. It became a subject of mathematicians, mostly. And French and Russians sort of battered and shattered this field and developed new language, mathematical language, and took it to a height where it became a little bit more elusive for physicists, because now they cannot even understand the language. By the time then cam theory comes, which sort of again reignites the interest. But the mathematics was far away from the students of physics, because they were not trained in the language. Then in 1960s early, the concept of chaos came. Once the concept of chaos came, well, the concept of chaos was much earlier to that, known to mathematician, but in 1963, yes, there's a guy called Lorenz, L-O-R-E-N-Z, you must have heard about butterfly effect and things like that. His contribution was, he showed that chaos can occur in very simple physical systems. That's where physicists start getting interested. This is a bit of problem with physicists. You want to always connect with real world applications. This is good, but sometimes this holds you back from attacking the problems which could have something to do 100 years from today. But you cannot blame physicists. That's how they are. So then they started to get interested in that. And then they thought, let's read the literature. When they started to read the literature, it was humongous. The mathematics was very problematic. But still interest started, because luckily at that point of time, there was another beautiful theory which came up, was the denomination group. And people were interested in what are known as critical phenomena, trying to find out universal exponents in gases and liquid, things like that. So interest of physicists was whatever they know, can they now use that to understand chaos? And it went up to, let's say, 81, 82. Then comes another problem. Whatever physicists could do, they had almost done. And then they understood that to do something more here is an extremely hard thing. Moreover, it required so much of computation that I don't know about physicists outside, but at least physicists in India were not very open to numerics, and that still happens to be case in age-old places in Calcutta. If you touch numerics, you are not Einstein, and then you don't attack problems which does not have any numerics there, which have lots of numerics there. So people sort of don't attack those things. People will only do problems which are so theoretical that you can get away with numerics and all. But there's no way out. Even as Suratna was telling you, that even in now gravitational theories and all, you cannot do anything without numerics. So chaos now became a subject where doing something analytically was extremely hard. You have to do lots of numerics, and you have to figure out things in that way. Mathematics can still be done, but it's very hard. Finding some very good theorems and lemma is not as easy. So a demonstration of chaos would be this. So this is a double pendulum, right? So this is one rod which can swing. This is another rod which can again swing. We can model it as a massless rod with some bob at the center of mass and a massless rod with a bob. The standard thing, right? Now this, forget about frictions, this and that, and think we are performing this experiment in space. Space will be a problem. Let's say in vacuum, but there still is gravity. So if there is vacuum, then you don't have any air friction. And this hinge is as smooth as possible, so you don't have any other friction like that. So it's a conservative system, right? And you can find out this kinetic energy, potential energy. What is going to be kinetic energy? You have to first find out the generalized coordinates. What are the generalized coordinates? How many generalized coordinates are there? 2, because it can move in 3 different directions, it can move in 3 different directions, but there are 2 constraints for each of this. So n minus 2, which is n minus 4, that is 6 minus 4 is 2. So you need 2 generalized coordinates. The best generalized coordinates to use here are the angles. I mean, I wouldn't call them best, because anyway, even if you use angle, you cannot solve the problem. Fine, whatever. Using angle is, let's say, convenient. Now you want to describe a motion like this. Let's say I take, so these are 2, well, by the way, this is not a double pendulum because you have 2 pendula, right? Because this is one double pendulum, this is another double pendulum. So I have 2 double pendula. Now I take both the pendula here. Okay. So they are oscillating the way they should. I take it back again. They are doing exactly same thing. Determinism. Same cause, same effect. See, if I am starting both the pendula at the same point with same velocity, initial velocity is 0, and if I start them at the same position, what the position will be? It will be specified by theta 1 and theta 2. And then they will do the same thing. This is determinism, nothing more than that. Now, look at this. Okay. Note what I am trying to do. Let's say I am trying to keep it. Let's make it more. So almost the same cause. Note the motion. They are not performing similarly, right? Well, there is coupling and all. This is not a perfect setup, but I can assure you, even if you make perfect setup, similar thing you are going to see. Okay? So they are behaving differently. So what happened to my philosophy? Same cause, different effect. Right? So should now I change my philosophy to same cause, different effect? And then what happens to my equation of motion? Because I know it's a conservative system, so I can write down Hamiltonian, which is time independent. None of the parameters are time dependent. What are the parameters? Length, mass, masses, gravity. All of them are parameters constant. Hamiltonian will be described by 4 canonically conjugate coordinates, 2 thetas and 2 corresponding momenta. And I know what the equations are like. They are the canonical equations. Then if I know the initial condition, I know what's going to happen next. Same initial condition, same prediction, same future. Not happening. Yet again, same. It's not only different, it's vigorously different. So what's happening? Should I change my philosophy? Now I'm going to convert my religion. This is the time. Nothing happens according to physics. There is somebody sitting up there, kicking this guy more, that guy less. because this one has committed more pop and that one has committed less pop. What should I do now? This happened, I mean, this confusion crept in because this doctrine of same cause having same effect got diluted over years. I mean, this was being thought right from the beginning. I mean, you slap someone, you get slapped back. But it's rarely you slap somebody and he hugs you, unless it's in a movie, Munna Bhai or whatever. So what happened now? You see how it got diluted. People started replacing the word same by similar as time went on. So you say, okay, this I take and it does this. If I almost take it there, it almost does the same thing. Right? So same effect, it's not same effect, same cause. It's similar effect, similar cause. Because first time I do this, next time when I try to do this, I cannot exactly start from exactly same initial condition. There's a little bit of problem. Even if you do it numerically, you will have computational errors. If you do in lab, you will have fluctuations from environment, things like that. You can never start at same initial condition. Same thing happened here. Though I am saying that I am starting with the same initial conditions, I am not. And if I am not starting with same initial condition, I am getting different effect, which is fine. So that philosophy is fine. What is confusing here is similar cause, but this is similar, almost similar. Similar cause is not giving similar effect. So the doctrine always was same cause is same effect, but when people diluted it and sort of memorized that similar cause will have similar effect, that's when this confusion starts. It never has to be that similar cause has similar effect. Similar cause can have drastically dissimilar effects. That's what you're seeing here. Okay? And you cannot now predict what is going to happen. You think, okay, now I can predict how this motion is happening. You do something. When you ask the experimentalist to repeat the experiment, he will try to start from there, but he cannot exactly at that point. He will get some other loop, some other way that things are happening. This ultra-sensitive dependence or initial condition of a system is chaos, very loosely speaking. How can you? What do you do in computation? How do you specify a point in computation? But you first declare in what precision you are going to work. So you always have error if you are working double precision in 17 digit. So 17 digit is not in your hand. So you cannot. That's the problem. You cannot know how things are happening simply because you don't have control on anything. But it has nothing to do with environmental fluctuations and anything like that. It's not because of statmech. It's not because of many molecules hitting it. It's simply because the structure of equation is weird. If you now, you can try to do this problem. You can write down Lagrangian. You should be able to write down Lagrangian. This is a common university question you are going to find in your probably first year exam. So you better do it first year or second year exam. A standard question. Write down the Lagrangian for double pendulum. Once you have Lagrangian, you can write down equation of motion because you know all the Lagrange equation. Sit down, take derivatives, dot, 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 you will get some weird looking equation. Now, look at those equations once you have got them. They look so weird, so many nonlinear terms, you don't know how to solve them exactly. And if you cannot solve them exactly, you cannot predict. And why you cannot solve them exactly? Because in this case, it is a 2 degree of freedom problem. The only conserved quantity you know about is the energy. The other conserved quantity is hard to find here. Actually, nobody knows. And probably there isn't any. But I don't know whether you can prove there exists no conserved quantity. Okay. So it's a system which you cannot solve, and all the things, I mean, start here. So such kind of systems are a problem in Hamiltonian formalism, things like that. It's not a problem. You cannot deal with them this way. Asking questions like its prediction does not make sense so much, because you see, experimentally you cannot even repeat the experiment. Then you can only talk about you have to ask different questions now. You cannot ask questions like, if I start here, where the particle will be. Because you can ask that question, you will get some results if you do numerically, but you cannot never repeat that experiment. So this is what chaos is all about. Different initial conditions are going to give you different results. But it's little bit but that's true for every system. Different initial condition will give you different results. So what's more here, that almost same initial condition is going to give you drastic different results. That is chaos. Now, never say chaos is randomness. That's again a big mistake. Randomness is something stochastic. You have no control on. Right? This is the standard example I usually give. It's a little funny and it makes sense. So there is some guy, let's say Mr. Sharma or something, he has a football. He takes it and places it right on some very busy road, okay, right in the morning while going to office, because he was not able to handle it. So he thought, I'll keep it here. While coming back from office, I'll take it. I mean, office is usually of, from 9 to 5 or 10 to 5, 7 hours. You can just imagine what can happen to the ball. Somebody comes, kicks it, some guy picks it, takes it in a car, some guy steals from the car, then the ball goes somewhere, it goes in some drain, then flows with the drain. Maybe at the end it reaches in front of Mr. Sharma's home, who knows. One of the possibilities, still a possibility. And then Mr. Sharma sees this, if I keep the ball on that square, it comes back to my home by 5. Why should I carry this ball every day? And so next day he takes the ball, keeps on the square. And then comes back and trying to find in the drain where is the ball. Not there. Why it's not there? Because there are so many external factors acting on the ball for 7 hours that you don't know what is going to happen to the ball after 7 hours. These are random effects. You don't know what the guy who wanted to kick the ball was thinking. If he was very happy, he sort of cajoled the ball and kept it there. He was angry, he kicked it at the face of some other guy. You have no control. These are random elements. So starting from the same initial condition, ball being on the square, 0 velocity, 2 degrees of freedom, ball can move, or 3 degrees of freedom actually. So 3 coordinates, 3 momenta, and it can move in any different direction. Right. So that's saying what? That you cannot predict whether you are going to, Mr. Sharma is going to get the ball in front of his house at 5 o'clock. In most of the cases you won't. But then you cannot say the motion is chaotic, because this was due to random external factors. So chaos is not randomness. Then how come chaos is associated with randomness and unpredictability? Because if you cannot predict, you will think it's random. I mean, what is the characteristic of randomness? The characteristic of randomness is you cannot predict. If you know what is happening to a system at this point, at next point what is going to happen, if you keep on repeating experiment, you are going to get different results. You feel it's random. Same thing is happening here. You keep on repeating the experiment and you get different results each time you repeat the experiment from nearby initial conditions. So you feel it's random. You cannot predict it. But it's not random in that sense. It's because initial conditions are different. It has nothing to do with stochastic variability which are coming in because of some guy hitting it. So that is chaos, okay, in very loose sense. But as I told you, before trying to relate this with any other subject, try to know the subject first and then ask those sort of questions. Because this is quite technical, how to define chaos. I mean, even in 2016, there was a paper which was trying to define what is chaos technically. Okay, defining chaos is hard. There are technical problems. So this is what I want, and this is probably the right point to end. What we have done here is a lot of things, but with very simple systems. We have started with action principle, we have done Hamiltonian, we have done canonical transformation, and we have seen that systems like these appear. Okay? Now you can do whatever you want to do, but try to find out this Lagrangian. This is a standard university problem. You will find it in. This is a suggestion, last minute suggestion. Okay? Great. So here is where I'm going to stop. Thanks. If you have any question, you can ask.